Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video, we're going to take a look at finding integrals using the exponential form. An exponential form is one more pattern of integration that we can use to integrate certain functions. Let's start by recalling what the derivative of an exponential function is equal to. If we were to differentiate this with respect to x, we would get e to the u times du dx. If we multiply through by dx, we get dy equals e to the u du. And if we integrate, the integral of dy is y. That will be equal to the integral of e to the u du. Let's reverse this. So the integral of e to the u du is equal to y. And remember how we defined y. Therefore, the integral of e to the u du is simply equal to e to the u. And if it's indefinite integration, we'll add a constant. So this is the formula you're going to use if you do encounter an integral of e to the u du. Again, we're going to be using the derivatives of transcendental functions to do these integrals because we have to recognize what the du factor will be for these functions. So make sure you have something like this handy. Let's take a look at some examples. In our first example, you could move the 5 outside the integral sign if you want. We know we're going to be using the pattern e to the u. So we're identifying u as 2x. The derivative of 2x is 2, so the differential is 2dx. I'm missing that 2, but that's fine. If I multiply by 2, as long as I divide by 2, it balances. That's my du factor. So now I can plug into my pattern, and this integral will be 5 halves e to the 2x plus c. You can always check by differentiating this to see if you get this. In my next example, I'm going to express my e to the u first and assume that this other factor is going to be part of my du factor. Let's see. So if this is e to the u, I'm identifying u as negative 4x squared. Therefore, the du factor will be negative 8x dx. We have the most important part of that. We have the function part, but we're missing a factor of negative 8. So we can multiply by negative 8 as long as we also divide by negative 8. Now I have my du factor exact. I can integrate this. It will be negative 1/8 e to the negative 4x squared plus c. Let's try some more. My next example, if I'm looking at the pattern e to the u is 4 sine x. So the du factor will be 4 times the derivative of sine of x is cos of x dx. So I have cos x, which is the most important part. The 4 I can introduce as long as I balance it. And I can balance it outside the integral sign. So there's my du factor. Now I can plug into this pattern. So my integral will be 1/4 e to the 4 sine x, and we'll add our constant integration. Any of these questions could be definite integrals where we have a lower limit and an upper limit and we evaluate, as we did previously with definite integration. Our next example looks very complicated, but what we're going to do is break up our factors and write e to our function first. So we'll write this as e to the inverse tan of 3x, and then we'll have 1 over 1 plus 9x squared dx. So we're going to look to see if this is part of the du factor for this function. So we're identifying our e to the u. Therefore, u is inverse tan of 3x. The derivative of inverse tan of a function is 1 over 1 plus that function squared. And then the chain rule tells us we have to also multiply by the derivative of the function, which is 3. So our du factor will be 3 dx over 1 plus 9x squared. We almost have it. We just need to multiply by 3 and then we'll have it. So if we multiply by 3, we'll just divide by 3 as well. Now we have our du factor, so we can integrate this according to our pattern. It will be 1/3 e to the inverse tan of 3x. Let's look at a couple more examples. In this next example, I'm going to separate the factors. So I'm going to write e to the natural log of 2x, and then I'm going to write that as 1 over x dx. So I just want to separate them so I can see if indeed this is part of my du factor. I don't want to leave it in a fraction. So if this is my e to the u, my u will be natural log of 2x. And the du factor will be 1 over 2x times the derivative of 2x, which is 2 dx. So du, the 2's will cancel, will be 1 over x dx, which is what I have. No manipulation required, so I can integrate this using my pattern. It will simply be e to the natural log of 2x plus my constant of integration. Now sometimes you're going to have to do more manipulation to use this pattern. So if we take a look at this example, what I'm going to do is I'm going to separate everything. So I'm going to pull the 3 out front. I'm going to write that as e to the negative 1 over x, and I'm going to write this as 1 over x squared dx. So I just separate all of the factors. So if my pattern that I'm looking to use is e to the u, I'm defining u as negative 1 over x, or in other words, negative x to the negative 1. So the du factor will be the derivative of negative x to the negative 1, which will be negative times negative, which will be positive, x to the negative 2 times dx, which is the same as 1 over x squared dx. I actually have that. So again, no manipulation is required in order to make this exact. It already is exact, and now I can just integrate. Don't forget about the 3, so it'll be 3 e to the negative 1 over x plus c, or that could be written, if you don't want a negative exponent, you could write that as 3 over e to the 1 over x plus c. It's going to depend on what's required in your course. Now I just want to give you a little bit of a warning. Just because you see e in the function does not mean that it's following this pattern. So I'll just show you a couple of examples where you could see e, but it doesn't mean that you're going to use this pattern of integration. In this example, what I have is a power in the denominator and then an e to the 3x in the numerator. Again, I'm going to split this up and I'm going to write this as a power. So it will be e to the 3x minus 1 to the power of negative 1/2. Square root means power of 1/2, and when I take it out of the denominator, it becomes negative. And then I'll write the rest of the function. So this, I'm not going to be using e to the u. If I just had this, I would use e to the u. But because I have this function, which is a power, then I'm hoping that this happens to be part of the du factor. So the pattern I will look at using is u to the n, where u is e to the 3x minus 1. So the du factor will be e to the 3x times 3 dx. So I just need a 3 here. I need a 1/3 here. I've got my du factor. So I'm using the function u to the n du, which is my general power formula. So that will be 1/3. When I add 1 to my n, I get positive 1/2, and I divide by 1/2, so that gives me a positive 2. My function will be raised to the n plus 1, which would be 1/2 plus c, and then we could just simplify that. That's that integral. Similarly, this example, we're going to separate. This question looks very similar, but in this case we had the square root in the denominator, so when we wrote it as a power, our power was -1/2. If we were to write this as a power, the power would be -1, which means we can't use the general power formula, we have to use the logarithmic form. So the pattern I will be using is 1/u. We're still defining u as 3x minus 1, du is still 3e to the 3x dx. So I still need to introduce that 3 and balance it with 1/3. Here's my du factor. But the pattern I'm using now is different. It's the basic log form. So this integral will be 1/3 the natural log of the absolute value of e to the 3x minus 1. So be careful when you do see the exponential function. It might be the exponential form of integration, or it might be the basic log form, or it might be the general power form, or some of the other ones we're still going to be looking at. So just be careful when you're trying to determine what pattern you're dealing with. Practice these as much as you're able to, and then when you're ready, we're going to move on to some basic trig forms of integration. Take care and see you then.